So in class we started challenge problem 3172, but it was a little too long to finish it, so I'm going to do it here. And we're going to start over and rename that separation between the wires. The book calls it A, but that causes major trouble. So the problem was that we have two stationary wires like this at a separation L. Let's call it L. And there's a slider on the wires. There's a piece of metal that's free to move along the wires. It has mass M and resistance R. And we apply, we put a battery basically here that applies a little EMF E applied, we'll call it. So we make a closed circuit. We have a battery here connected to wires, stationary wires, and then to the slider, which is also a conductor. Current can flow all the way through. So we have current flowing around like that, because this is the positive part of the battery, and that's the negative part of the battery. And the problem is, the book wants you to show that the velocity that this thing will move, v, changes in time. It'll move to the right, it'll change in time, it'll become E applied over BL times 1 minus E to the minus BL squared T over MR, the mass times the radius. So that looks like a fairly complicated expression, and getting there is fairly complicated. What it really means, though, is this is telling you that something will grow from rest to a finite velocity. That's what this function does. At t equals 0, this is e to the 0 is 1, 1 minus 1 is 0. So it starts out at rest, velocity equals 0, and it grows to a finite value, because when t becomes infinity, when t becomes large, this goes to 0, and it just becomes E applied over BL. So it's complicated because it does something that looks kind of like this. Velocity versus time, and 0 just kind of goes up like that and saturates out at E applied over BL. Okay, so how do we do it? Well, first we would say what? The E applied creates current. Right, that has to happen to get things started. If there's no current flowing, there's no nothing will happen. Let's see. Oh yeah, of course. So there's a magnetic field, of course. So there's a magnetic field sticking out of the wall. I knew something was missing. Okay, now we're set. Okay, so E applied creates current, and the current that you get I is E applied over the resistance. Right? So that's just similar to V equals IR. And then, if we have this slider has current flowing through it like this, and it's in a magnetic field, it's going to experience a force. Right? So E applied creates current. The slider feels a force. What? F equals IL cross B is what we usually say. And in this problem, we have L is down. L is basically the length of the slider is the magnitude of L, and it forces the same direction as the current, so it's down. L and then crossed with B has to come out. So my fingers have to move towards B. So we realize that F is the direction that we want it to be. F is pulling this thing to the right because it's current in a magnetic field. So it's equal to I L B. And if we define our x-axis as starting here from rest and going that way, then it's in the I-hat direction. Pulls it to the right by ILB. So at this point you could think you're finished. You could say, well, that equals to MA, and acceleration is dv dt, so you could have some expression for the time rate of change of the velocity and just do one integral and get it. But that's actually not quite right, because in addition to the EMF that is applied by the battery, there's also another EMF from Faraday's law. There's also an E induced that's equal to minus d dt of integral So we have to consider that in this current loop, there's two EMFs, and actually they're probably going to cancel. This one is positive going this way, this one will probably come out negative, and will make the current go down. So in the end, the EMF and the current depend on the velocity, because how fast it's moving tells you how fast dA changes. And that's what makes the problem difficult. Okay? So let's start going. First, let's calculate what is E induced. What is the EMF that gets induced by this motion? So the EMF induced is what? So EMF, what we just wrote, it's minus d dt integral of E B dot dA. Let's see. But as we know, we always like to have B parallel to dA, right, which is the case here. The A vector, if we're going positive this way, points out, and B points out, so they're both out. And if we just change the area, that also points out. And also B is a constant. So that lets us ignore our vector calc, as we always like to do. This is just B dA, B comes out the integral. We have the integral of dA. So the E induced is just minus B times the area. Okay? What is the area? Well, if we put the origin all the way over here, the area is just the x position times L. So it's minus BXL. All right. Let's see. Oh, wait, I'm sorry, ddt. Dropped my ddt. Something was wrong. ddt. So minus ddt of BXL. Okay, so which one of these three can change? B cannot change. B is a constant. L does not change. L is a constant. Clearly, it's x that changes. So E induced equals minus BL dx dt. What is dx dt? That's the velocity. That's what we're looking for. Okay. So minus BL B. So the induced EMF that's going to cancel the applied EMF depends on how fast it's moving. That's why we get such a complicated result. Okay. So let's get then, so what is the corrected look at our corrected current. It's I equals the EMF applied plus the EMF induced over R. Or we could write it this way, let's go ahead and just write the whole force, F, then the corrected force is this, it's I, L, B. So it's I, which is E applied, minus, we're going to add E induced, but E induced was what? It's minus VLV over R. So there's the current, the new current. I, L is L and B. Okay. So there's the force down there. Now, let's just keep that down there. Erase the rest of this. Keep going. Page 2 of 4 pages. Let's see. Okay, so we're trying to solve for V. The question is, how does it depend, what is V as it depends on time? Okay, so we just apply the definition of force, right? So force is ma, but that's m dv dt. Okay, so if we have m dv dt equals, let me separate these out, equals E applied LB over R over R minus BL squared over R times V. So now we have an equation where we have dV dt equals some function of V. So that's not a simple equation to solve. That's that's one of these differential equations that you have to figure out a trick to solve. You can't just integrate this with respect to t, because integrate this with respect to t, you would get the v. But then you can't integrate that with respect to t because you don't know what it is. Right? That's the function you're looking for. That's varying with time. So that's the tricky part. So the trick in differential equations is to get all the v's on one side and all the t's on the other. And you could do that by dividing by v, multiplying by t, but this term is in the way. Right? This term is going to keep always a mix between the v and the t. You'll never separate it perfectly with v on one side, t on the other, so you have to change variables. And we'll use u equals something. We're going to put this thing up here. U equals e applied minus b L v. And that will actually let it work out. We're basically setting the change of variables equal to this thing, because this is the problem. If we just had a constant here, or I'm sorry, if we just had v here, and just had a single term, it would all work. But we don't. We have these multiple terms. So we're setting the new variable to be this whole expression, e applied minus BLV. And that'll let this work. We also need to be able to plug in addition to that, we need a du dt, because we also have dv dt. So we just take the derivative of this thing with respect to time, that's 0, and that's minus b L dv dt. So now we have our two expressions that let us change variables. So let's see, how are we going to use them? So we could plug them in here, and unfortunately I wrote this, I switched it up so you can see that this was in the way, but this is really the form we needed it in. So I'm actually going to erase now and rewrite the equation we're trying to substitute into here. Sorry, I only have so much room. So we're really trying to substitute into this. M dv dt, right, that's ma, equals e applied minus b LV over R times LV. So this is what we're substituting into. So it's M times dv dt. What is dv dt? You just bring these over here. It's minus 1 over BL du dt. Minus 1 over BL du dt. Okay? That's why we had to take this derivative, so we'd have something to substitute there. This is what we made equal to u, so this is just u over R L B. And now we have something that we can sort of get all the u's on this side and the t's on that side. Okay? So we can get this down to du over u, du over u. Right, this came over here, equals minus, we'll put everything else on the other side that we can. What's going to come over there? BL, there's another BL squared over R, and then there's a dt. So du over u equals BL over M R squared. I lost it here. There we go. So there we go. Now this is a differential equation that we can deal with, because we can integrate both sides from some initial condition to some final condition. I'm going to write my u over here, because we're going to need together, equals e applied minus b LV. So now we have, won't forget u, force anymore. So now we've used our force equation, and we've written it in terms of velocity. We've substituted variables. Now we're going to integrate both sides from some initial condition to final condition. So we're going to integrate from some initial time 0 to final time t, which is from some initial value of u naught to some final value u. That's how you would do that integral. This integral of du over u is the log, natural log of u. And if you apply the bounds, you get basically the natural log of u over u naught. Okay, so go do that integral. Maybe you've seen that integral before. And this is the integral just a constant times dt, so this just becomes minus the constant t, and we evaluate it from 0 to t, and of course the 0 goes away, and we just put a t there. So this is telling us how u depends on t. What we want is how v depends on t. We'll get back to that in a minute. Let's go ahead and write it a little nicer. Let's take the exponent of each side. E to the natural log is just the argument. So u over u naught equals e to the minus BL squared over m RT. then, let's see, we can we'll go to the last page here. And now what we want to do is go back to V. Okay? So let's see. Let's see, U was what? E applied over BLV. E applied minus BLV. There's the V we're looking for. What was U naught? Let's see. U naught was what's going on with U when t equals 0. When t equals 0, U naught was just E applied. Okay? It's just what's going on E applied. Or you can say, look at it here. When t equals 0, V was 0. So that goes like that, and U naught is just the applied EMF. So it turns out, we didn't say it before, but that U, it's an EMF, or it's in units of volts. So here we just write E applied. So that's that side. And then the right side has no U's in it. It's just E to the minus VL squared over T. So that's the exponential decay part. Okay, now we just solve this for V. All we got to do, let's start erasing up here. Let's see. Solve this for V. This is 1 minus that over E applied. Then we bring this over here, leave the 1, pull that over there. So let's see, let's do all those steps at once. V, LV over E applied. That's going over there. The 1 stays here, and the exponent comes over here. Minus E minus VL. We've written this 100 times now over MRT. All right, and then now we just need V as a function of T. V equals what? V, put this on the other side. V applied over VL. Over VL times 1 minus E is a minus VL squared over MRT. And that matches, hey, what do you know? That matches that.